Hey, good afternoon, Dr. Burke.
Good afternoon, Dr. Haishun. You are welcome. How are you?
Very good. How about you?
Thank you.
And what time is it in Turkey now?
It is 7 to 5 o'clock p.m. Almost 5 o'clock p.m.
Okay, not too bad.
Okay. We will start almost in 5 minutes.
Okay, good. And how many people do we expect?
Usually 50 to 100.
Wow, so many.
Let's check, because some of them are participating through YouTube.
Okay.
Some of them will appear here right now at Zoom platform.
Mm-hmm. And how much time do I have for the talk? 30 minutes or 40 minutes?
Between 30 minutes to up to 40 minutes, because we need some time for the questions and the discussion.
Yes, of course. Yeah.
Usually
so the whole,
10 to 15 minutes.
Yeah, the whole program is for 1 hour or for 50 minutes?
Usually around 50 minutes, but
Okay.
If we require some more time, it can be extended up to an hour time.
Yes, of course. Yeah, I understand that. Okay, that's good. Yeah. I will try to keep it in time. Yeah.
Okay, thank you.
Can I share my screen right now?
Excuse me?
Can I share my screen right now?
Yes, sure. I have already assigned co-host.
Okay, good. And let me put it into presentation mode.
Yeah. Usually many of the participants come here within the last few minutes. And
Okay,
in
that's
many
fine.
cases, in the first 5 minutes.
Vậy ini crop ya.
Can you see my screen right now?
Yes, it is visible.
It is in the, I've already turned to the presentation mode.
Okay.
Does it show correctly?
Yeah, it is in the presentation mode. It seems it's visible in full screen mode. So
Okay.
it's presentation mode. Let's wait for...
Yeah, okay, no problem. Yeah, just let me know when it's ready.
Yeah. Just a moment. Professor Lipping has not participated yet. You know, Professor Lipping is the president of Agromatics Society.
Yeah, I know. Yeah.
we usually start after his participation. And first, I will introduce Agromatics Society and your presentation. Then afterwards, you may keep going on your presentation.
Okay, good.
Professor Lipping, you are welcome.
Yeah. Hi, Berg. Good evening. Your time is afternoon, is right?
Yeah, it's 5 p.m. here in Istanbul.
Uh-huh.
And good morning to you.
Yeah. Good morning.
Hey, good morning, Liping. This is Haishun.
Yeah, Haishun, good morning. Thank you for giving talk.
Oh, my pleasure. Thank you. Thank you for the invitation.
Okay. So I guess we will have rapidly increasing amount of participants within the next few minutes. It usually happens in that way.
Yeah, now we have 33 people already. So.
And how many countries do the participants or members cover?
Maybe over 20 or maybe over. But this particular we don't know because we send out to all the membership of the society. So.
Oh, okay.
Yeah, but how many people? Maybe I think maybe more than 10 countries participating.
That's pretty good coverage.
Yeah. It's now 35 people.
Yeah, it will increase up to at least 50, and we will have some other participants in the YouTube channel as live here. So, Professor Lipping, shall we start by introduction to Haishun?
Yeah. We should start. Yeah.
Okay, just a moment. Okay. Hello, everyone, again. Thank you for joining us, and welcome to the 6th Agromatics live webinar. And as you know, my name is Haishun Yang, and I'm the Vice President of International Society of Agromatics. Professor Liming is together with us. He's the President of the Society. And today we are welcoming you to the 6th of Agromatics webinar series. And today's webinar is entitled as Crop Digital Twin, its concept, creation, features, and actions. First of all, again, I suggest non-ISAM members to be registered to ISAM through www.agromatics.org so that they can be informed about activities of the Agromatics community and take the Agromatics Society's other future benefits. And I'm delighted that we have many valuable participants today in the webinar. And now, first of all, please keep your microphones muted. Questions may be asked anytime by utilizing the chat function. By the end of the session, you may also take the case that we may have your questions and answers orally. And although digital twins are increasingly told in many different fields, they are also raising questions about their practical benefit, applicability, or difference between modeling simulation and the twinning concept. And today's webinar subject is related to crop digital twin and its applications in agriculture. This webinar will cover the concept, formulations and features of typical crop simulation models, as well as examples of its applications. And as I have already introduced you, we have a distinguished speaker today. He is Dr. Haishun Yang. And Haishun Yang is a crop modeler and associate professor in the Department of Agronomy and Horticulture at University of Nebraska, Lincoln, UNL, in the United States. He obtained his MSc and PhD degrees from Wageningen University in Netherlands, and his expertise includes modeling of crop growth yield, soil organic matter turnover, carbon cycling, crop nutrient requirement, and recommendation and bioenergy system lifecycle analysis. He has published several computer simulation models, more than 60 peer-reviewed scientific articles, and book chapters. And he has taught crop modeling at UNL at the graduate level for more than 10 years. You are welcome, Haishun, Dr. Haishun, and please start your presentation.
Thank you, Professor Burke, for the introduction, and thank Professor Li Ping for the invitation. Hello, everybody. My name is Haishun Yang, and today's talk is about digital twin, or a more traditional term is crop modeling. I will cover in my talk several things, including basically the concept. What is a digital twin or crop model, and how they look like, and then what are the inputs and outputs from the crop model. Then, of course, probably you're more interested in the formulation of crop models and the applications of the models. And then I will end my talk with some remarks. First of all, what is a model? What is a simulation? By definition, a model is basically a simplified representation of a system or a virtual twin of its physical twin. So that's basically in the traditional term as well as in the modern fancy term. Crop model basically is a systematic representation of processes of crop growth and development, simply using, or not simply, but using mathematical functions. Simulation is the process of reproducing the essence of the system, but without reproducing the system itself. Basically, you don't need to create the physical world of the thing in order to basically go through the process. So through simulation, the essential characteristics of a system are reproduced in a virtual world, which allows us to study it in a more abbreviated time or spatial scale. Basically, you can study it in your convenient way. And how a crop model looks like. This is a part of the very early model, Morphos, which is the first product of crop modeling produced in Wageningen. And this is basically part of the input page of the model. And then another part of the input setting, that's crop parameters. And then now we have the digital or the output in a numerical way. Then, of course, you also need a graphic presentation of the result. Then we have a more modern crop model, the Hybrid-Maize, which is developed at Wageningen at the University of Nebraska. And this is the input setting on the front page. And then you have the numerical out page on daily time steps. And then you have a part of the graphic output, which allows you very quick examination of the results. And of course, a dynamic show of the results is also very important. So this basically shows you from beginning of the season, that is planting date, until maturity, how the canopy expands, how the biomass accumulates in different organs even. Now we want to see how the model looks like internally. Basically here is the model look in the assembly line. It's just like, for example, the circuit board of electronic devices. And then this is a more important part, that is the code. The code of the program, of course, before compiling. And typically, crop models require several types of input. The first one is the weather data, because the crop basically grows in response to weather. And for weather data, typically you need the daily data, including solar radiation, which is the power for plant growth, then the maximum temperature, minimum temperature, rainfall, wind speed, and humidity. All these parameters basically regulate the plant growth. You also need the crop genetic data, including the maturity, the photo period sensitivity. If some crops do have a relatively significant response to daylight, then you need a canopy light extinction coefficient, which is basically characterize the canopy shape for light inception. You also need the potential number of grains, which is a genetic, basically genetic potential, and also the potential grain fading rate, which is part of the crop growth potential. It's not the real one, but the potential. The real one depends largely on the environment condition and the growth rate. Then you also need the crop management data, including when the plant is planted or seeded, and then the planting depth and the plant population. At the same time, if the crop is basically water limited, or you have this possibility of drought, you also need soil information, because soil is the media for nutrients as well as water, including soil texture, the maximum rooting depth, and field slope, initial soil moisture, and the nutrients and organic matter, which of course is indicator of the soil fertility. Formulation of crop models actually depends on the complexity and the type of modeling. In the most traditional way, crop models describes the following processes. First is its development. The development is largely measured by growing degree day, or GDD. And it also shows the stage of the crop. Typically, for the important stages, including emergence and the V stage, which is the vegetation growth and the flowering, and R stage is for corn, is the part of the grain fading period and maturity. Then photosynthesis, of course, it's the essential part of plant dry matter production, and also including respiration and the biomass partitioning to different organs. Then we have the plant growth. Growth basically is the process of dry matter production and accumulation, including the biomass of each organ, leaf, stem, seeds, and the roots, as well as the leaf area, or we call it the leaf area index. Basically, it's the total leaf area above 1 unit of ground area. Then the water-related part, that is the evapotranspiration, including the root water uptake and the soil surface evaporation. Then some models can even handle nutrient uptake, because nutrient, of course, is a very critical part for crop production and yield. And then for most models, actually, the nutrient uptake is simulated or is considered as a function of a biomass gain or biomass accumulation, because basically more biomass it produces, more nutrients it requires. And one of the characteristics of the current simulation models is that almost all the calculations are done in a sequential way on daily basis. Of course, we know that plant growth does not do sequentially. That is, one step after another. For example, photosynthesis and respiration. Actually, they go parallelly. However, in the simulation process, parallel computing is still very difficult to implement. However, that is a future. the typical actions of crop simulation goes in the next way. First, you calculate the GDD or growing degree days and crop stage. That is largely follows the temperature. Then you have the water part, because the water part is one of the limitations of crop growth. You first calculate so that the later part, when it comes to dry matter production, this function will kick in. And after that, if the model can handle nutrient uptake will be simulated. Then you have the light interception by the canopy, and then photosynthesis. Then some models can handle also respirations, including maintenance respiration as well as growth respiration. Then you have a dry matter partition to different organs, and then you have finally the net biomass gain of each organ. Then, of course, we have handled all the dry matter part, but for plant, more crucial part is the leaf area expansion. That is basically the leaf area related to the leaf biomass accumulation. So that is basically the sequential process of simulating a plant growth. Not only crops, but all plants, basically. Now we come to the applications of a crop model. And that part I want to spend a little bit more time. Basically, you can use crop models in almost many different ways. But for this talk, I want to cover 4 aspects. One is how to predict crop growth and yield. And then, of course, that prediction largely for the purpose of optimize plant management. And at the same time, you can maximize your yield. Then in the US, the agriculture extension is a very big part of the research, and we use crop models to help the extension education, because that helps explain the process and explain how to optimize your crop management. Then for researchers, the crop models can be a big help to explain the processes and search answers for questions. The first example is how would maize, or in the US we call it corn, how maize yield increase with the increase of plant population. For people familiar with the crop growth or crop yield, they all know that plant population is a big factor affecting the final yield. However, too low population or too high population don't work either. You need to find the best population. Then if you do a traditional research, for example, you have 3 different plant populations. At the end of the season, you measure the yield. And in this case, we have the 3 populations of 20,000 per acre for corn. I'm sorry for the US or the English units. And then another level is 25, and then you go up to 30,000 per acre. If you do a research like this, you will find the result like this. It's almost like a linear increase of maize yield with the increase of maize plant population. This, of course, this graph is produced by simulation. But if you do field research, you will get similar results in a very likely way. Then, can you apply this almost linear rate of yield increase to increase the plant population? Well, actually, many have died because this is the result, how the result showed us using this run. But if you extend the plant population to a higher level, that may not be the case, actually. Then, using simulation, you can do the next level or increase further the plant population to see how the yield would respond. In this case, actually, the response is not like the yield increase from 20,000 up to 30. when you further increase it to something like a 50,000, actually the yield gain is much less. So this is something, if you don't use simulation model, you will not find. Of course, you can do the research in the physical world, but it's very costly and it takes a lot of time, a lot of effort. If you have simulation model, then you can do it very quickly. So if we further look into this response curve of yield to plant population, you can find that when the population increased by 5,000 from 20,000 to 25,000, and then the yield increase is 31 bushel per acre. Sorry again for the US unit. Then if you further increase the same 5,000 plants per acre to 40 to 45 or 45 to 50, your yield gain for the same increase becomes very minimal. So that tells you the efficiency in increasing yield by increasing plant population. And if you assume the response is the same when the plant population is higher as the lower part, actually you will be totally surprised. So this is one example of a quick use of simulation model to find a better answer. The second example is, when is the best time to plant a crop? In this case, we use eastern Nebraska and corn again as example. You can do similar thing. Actually, this kind of experiment has been going on for many, many years in the publication, and you can find a lot of papers on this topic. And it seems there's no end of the search. However, if we do simulation, in this case, we do 3 years, and we do a different planting date in the field, ranging from early or middle April, that is earliest time you can plant the corn in eastern Nebraska, until late May. That is the latest. Otherwise, the plant will not go into maturity. So in different years, you will find the response of yield to planting date is somewhat different. Without taking the first year, that is in this case 2013, and it looks like the yield is highest with the early planting date here in early or mid-April or early May. However, for the next year, the response seems opposite. The later planting gives the best yield. Then it becomes difficult to draw the conclusion if you do a physical experiment in the field. However, if you do many, many years, in this case, we did, of course, we use simulation again, we did 34 years. You will find in this environment, within the time frame of mid-April until late May, the yield actually does not change that much. Or kind of there's a variation, and over a long time, you see the yield is very similar if you plant the corn in this time window. Of course, in this case, it is irrigated. If for rain-fed situation, it can be different, because for rain-fed situation, the water availability or the rainfall can become a compounding issue. But in this case, we use the irrigated case. Okay. A third example is the irrigation water. How much water, irrigation water, is needed in any environment? In this case, the example is in the western Nebraska, which is the drier. Okay, this is a very common question for people who want to irrigate the crop. We use the Hybrid-Maize to do the simulation, and this is basically to show how much water the crop requires if it's fully irrigated. Means we provide water whenever it requires and to the amount it requires. So you can see it from this result that the crop requires over a long time, in this case 32 years, in the range of 600 to 700 millimeter water. Here the result is inch. So basically the crop requirement of water is relatively stable across years, between 600 to 700 millimeter of water. However, when it comes to the amount of irrigation water it requires, it is very different. So in this case, it ranges from almost no water is required up to 15 inches of water. So the variation is huge. And if you want to know why the irrigation requirement varies so much across different years, of course, the answer lies in the amount of seasonal rainfall. For years that have quite a lot of rainfall, of course, you don't need that much of irrigation. For dry years, you will need a lot. So this is kind of explanation of the water requirement is very useful, very handy when you use simulation models. The next example is how much nitrogen the crop requires. Nitrogen is the first or most important crop nutrients and very critical for most crop management. And in the US, it's very interesting. That is, until today, almost every state, agricultural state, has its own secret recipe for calculating crop nitrogen requirement. We are in Nebraska, and one of our neighboring state is Kansas. Both states are agricultural states. In Kansas, the formula of calculating nitrogen fertilizer requirements for corn is shown up here. It has the element for YG, which is yield goal, or anticipated crop yield. SOM is the soil organic matter content, and the profile nitrogen is the nitrogen that is present in the soil at or before you apply fertilizer. And then you have uncredited. Uncredited basically is the nitrogen that is brought into the system through crop residues like soybean. Okay, the same elements appear also in your Nebraska recipe, but the formula is quite different. You see, for the same crop, if you cross the state boundary, you should follow a different recipe. It's kind of interesting. We know that agricultural science should not be divided or should not matter to the political boundary or an administrative boundary, but in this case, it is. Because basically, both approaches are empirical. And then one of the good things about such a recommendation scheme is they're very simple and easy to use. Almost every farmer, no matter how good or how poor education they have, they can do it. It's very simple mathematics. The problematic part is that the yield goal first. Yield goal is the biggest driver for nitrogen fertilizer requirement. However, the yield goal itself is a big company because when you do the calculation, you have not planted the crop yet. And how do you know what kind of yield you will get? The second is there's no response for a specific season weather because the season is not coming yet. So how do you know how wild, how wet, or hot or cold the season is compared to the average? Okay, and also there's almost no insight about the mechanism of crop nitrogen requirement. So this is the problematic part. And we developed this Maize-N program using a systematic approach for the nitrogen rate recommendation. Here is the front page showing the input requirement. Actually, there are many inputs, but everything the crop or the model asks actually is known if you are a real farmer. Okay, so it's not a big deal. Then in this case, we use the model as example to simulate how much nitrogen is needed for field in Nebraska with following information. Yeah, organic matter content of 3% and fully irrigated and planting in the beginning of May and plant population is 32,000 per acre. Then the Maize-N program provide you not only one number, that is a nitrogen rate, but also a series of numbers to show you the different component of your field, your crop, your soil, before you get this number, the nitrogen to be applied. In this case, 109 pounds of nitrogen per acre. So the number itself actually is explained by all the numbers below it. We don't have time to go into details, but for anyone who is interested in nitrogen management, they will be very glad to see those numbers before understanding why you need 109 instead of 209. So this is more insight about the system itself. The final example is the use of simulation models can help us understand what the yield potential in a given system. This is the so-called question of yield potential and yield gap. This is more a matter of food security, because yes, right now, for example, on average, you can produce 500 kilos per area, but what is the potential of production, and what is the gap? Whether you are approaching the limit or there's still big room for improvement. So this is a very big question, especially for policymakers at a higher level, like a national level, even international level. And using crop models, and this we have a big project. It's called GIGA. It's the Global Yield Gap Atlas. We have come up with a map or database to show at country level what is the yield potential using advanced technology or plant management, and then compare it to the current actual level, come up with the yield gap, how much gap you still have, or where the gap exists, and then this will get your investment, your policy making, and several things. Here it shows, for example, the wheat yield potential at country level. Here is China and Australia and some other part. For example, you can see in China, the winter wheat yield potential is something like 6 to 7 tons per hectare. While in Australia, we know that Australia is one of the big wheat exports. And to many people, they may think that the yield of wheat in Australia is high. Actually, it's not that high. It's because, first of all, they have larger production area, and their own domestic demand is relatively low. As a result, they have a big surplus of wheat production. Their yield is only like 3 tons per hectare. It's only probably half of China, but they have a big surplus. And then you have a very high yield in Europe, like 8 to 9 tons per hectare. So that's it. And of course, in some dry environment, for example, here you have a pretty low yield. That's largely because of the limitation of water availability. Now I want to end my talk with some remarks about modeling or digital twin and their application. First of all, we see the strength of the model and modeling. Basically, it enables a systematic study of your system or your physical twin, especially its response and the interactions among its component and with the environment. And second, it helps identify the weak or wrong link in the system. That is basically answer the question in the scientific arena. Because if you use the current knowledge, you build the model, but the model does not produce the results you anticipate, something is wrong. That's like if you assemble electronic device using kind of for the circuit design, then it does not work, you will know something is wrong. So this is one of the kind of strengths of using simulation model. Then, of course, all simulation results are quantitative and repeatable. No matter when you write, where you write, the results should be the same as long as the input information is the same. And then, of course, it's very efficient in terms of cost, in terms of time consumption, and it's very suitable for education, research, and many applications. But as we know that every coin has two sides, okay? At the same time, we need to be cautious about using simulation models. First of all, models are virtual trained, and they are not the real world. They will never be. By definition, if a model is so good that it's as good as the real world, or the digital twin is the same as the physical twin, basically your digital twin has become a physical twin. It's not a digital twin anymore. So by definition, models are always somewhat different from your real world, okay? Always keep it in mind. But more scientifically speaking, all models have assumptions in their formulation. This is a very important part. When you apply models, you should know whether the assumptions are met or valid in your application. For example, in many crop simulation models, they assume there are no nutrient deficiency. However, if you apply the model in the situation that nutrient deficiency is significant, your simulation result will be wrong. So this is kind of things we need to be aware of. Then most functions for biological processes are only valid within the limit of the condition when the formulas are derived. However, when you approach the limit or go beyond the limit of the conditions, your simulation results will start to deviate from the truth. So this is very important. So don't apply models too much to the limit, or if you go beyond the limit, it will be wrong almost. Then, of course, people say, well, if you provide the garbage to the model, you will get garbage from the model. That is very true. But at the same time, actually, as a modeler, I also know that sometimes you put the real good information or data into the model, you still get something bad out. That's because the models may not be good enough to handle that situation. And the last one is very, very difficult and sticky to modelers is how to assess uncertainty on model results. Actually, this one is still a big debate scientifically, because whenever you produce a number, scientifically speaking, you should always give a kind of the range of errors. Otherwise, any number will almost be meaningless without the associated standard error, this type of statistic assurance about the simulation, about the data. That's all I have. Thank you very much. And I would be glad to answer questions.
Thank you, Dr. Haishun. Your questions are welcome now. Meanwhile, I may start with a question. As I also mentioned during the introduction of today's presentation, there is a confusion or a better need for classification between modeling and simulation and the digital twinning, I guess. So how do you interpret the difference when we consider some requirements, including specifying the, for example, modeling parameters or simulation parameters dedicated to the country, field, crop, as you have described, with respect to adaptation or adaptive alternatives to their coupling within the terminology when we use digital twinning? Simply, what is the basic difference or advantage of the digital twinning when we perform together? Because many people think that digital twinning is the new name, only the new name. When we combine modeling and simulation together, is it in that way for crop simulation, or is it possible to have some more advantages, especially in the way of accuracy, if we construct also an adaptive mechanism driven through the real-time monitoring of the model or models and simulation couple accuracy?
Oh, thank you very much, Professor Burke, for the question. Well, I will try my best. Basically, in my opinion, the crop simulation model, as I have presented, is a more traditional, is more conservative. What it means is it's less flexible. It shows you the, let's say, the fundamental processes it simulates, but it's less flexible to the real situation. While the digital twin, on the other hand, incorporates the concept and method of traditional modeling, but also adding more ways of dealing with the real world complexity by mechanisms like machine learning or the real-time calibration. So in my opinion, the current digital twins kind of build upon traditional simulation modeling, but also have added more ways to deal with the real-world complexity. So in this way, you combine the strengths and advantages of both ways. So in my opinion, digital twin indeed is the way forward, and also it can overcome some or big part of the shortcomings or hurdles of traditional simulation modeling. I hope I answer at least part of your question.
Yeah. Another question is, how do you see the accuracy management with the point of view of a farmer and the point of view of an agricultural management, such as a governmental level management? How much do you rely on the models in your decision-making mechanisms, or what is your suggestion for the future roadmap for utilizing the models and simulation? Do you think that better modeling and simulation supported through real-time data will be a part of continuing ongoing job that provides economic benefit to the governmental decision makers as well as the field operations?
I think, first of all, in order to judge the accuracy of a simulation model, we first need to know what is your space one, the variation of data in the real world. For example, when you want to apply simulation model in a specific field, you need to know how much variation this field has, for example, in terms of yield, or in terms of soil fertility or soil nutrient content. With that in mind, you can better understanding, okay, what's the requirement of accuracy for a model? For example, if the standard deviation of yield across the field is, let's say, is 1 ton per hectare, then if the simulation model gives you accuracy or error of 2 tons, that means the model is not good enough. However, if the simulation model can give you 0.5 ton per hectare error, that is probably good enough for the application into your field. At the same time, I think the real-time monitoring, especially by means of remote sensing, can be a very good addition to the traditional simulation model, because the real-time monitoring can provide not only a very good correction or calibration of simulation model, but can also add another dimension, that is the spatial variability. Because in reality, no whole field is uniform. We know that. The remote sensing, especially the high spatial resolution remote sensing can add very important component to the traditional simulation, which assumes everything is uniform. Okay, and then, however, the simulation modeling can provide an addition to the real-time modeling by providing kind of predictions, because real-time monitoring can tell you what it is now, but it cannot tell you how the things will look like tomorrow or the day after tomorrow. While simulation models, which is based on the principles or the scientific understanding of processes, that can guide you through how the things will look like in the future if conditions will be like this. So that's in my opinion, if you combine the both, you will have a far better outcome than the single one from either.
Okay, thank you. And I have another last question, if other participants don't have any other. Marginal efficiency management is usually one of the major problems. For example, farmers usually take decision about irrigation scheduling, irrigation planning. In your case, for example, you have given the case for maize growth. And what is the marginal efficiency management accuracy, probable accuracy, that you can take, for example, by using the modeling and simulation techniques in a feasible way that can be applied to the farms regarding to the current monitoring data level? And second, do you suggest that to take as a service? For example, the strategy is important, and the model usually, you know, in the farmer's level, modeling and simulation tools cannot be run in an efficient way or in practical use, because many computational tools will be required and so on. So as a service, in my second part of the question, as a service is the current trend to reach to end users, you know, and, you know, AI as a service, software as a service. So this digital twinning as a service may take place through the apps connection and the monitoring systems connectivity as a part of telemetry economy. Do you think that it may be an ease of use or probable feasible future for field farming, you know, reaching to farmers by connecting through apps and the monitoring tools over common computational tools by providing the models and the parameters as a service? This is the second part. And do you think that it will, in this way, be effective tool in last few years?
I will first answer your second part. That is the feasibility of using models by end users like farmers. Yes, actually, we developed a crop irrigation scheduling tool called CornSoyWater. Basically, it's irrigation scheduling for maize and soybean. And to use that, the farmers only need to provide a few field-specific information, including what is the maturity of the plant, of the variety you have planted, and when you planted your crop, and basically and plant population. That's it. Of course, for using the simulation tools, you need more information, including the soil texture, including the daily weather data. Especially the data manipulation is a big hurdle for most cases of using simulation models. But in our case, everything is already prepared automatically by the program in the background. For example, once the farmers have selected the location on the Google map, their field, the program will automatically identify the closest weather station. And then program will get the weather data right away for your field and prepare the data. And then the soil information comes from online soil database for the soil texture and other information. So almost everything is prepared except your field-specific, crop-specific information that should come from the farmer. And with that, actually, the model will show you result in a fraction of a second. Actually, the farmers even don't know there is simulation, don't know so much information is already prepared in the background. So basically, it backs to the question or to the requirement how we as researchers, scientists, prepare or develop such tools for the end users in their mind. You see, in this case, yes, the tool actually is very convenient. It's just like using, let's say, using the driving navigation in your cell phone without too much trouble. Almost everyone that can read the words on the screen can do it very easily. Of course, it doesn't mean every model right now is already developed this way, but that's the way to go. And for the farm service, the first part, I believe, yes, actually the monitoring situation, well, the real-time monitoring, again, as I said before, should be combined with the process-based simulation model to provide the best of these two worlds, or these two parts, basically.
Okay. And meanwhile, Dr. Yang, Jangui Yang has a question. Please, Jangui.
Me, yeah. Hello, can you hear me?
Hi, John.
Okay. Okay, good. Thank you very much, Professor Yang. Very good presentation, and really, I really enjoy it. Yeah, yeah. I have some question that really, trying to get some help. In most of that simulation and modeling case is that we always look at that field level or point level, modeling and simulation. In our case, our use case is we are looking at a regional modeling and simulation. So the biggest problem is that in a regional level, we really don't know, every farmer's, production management practice, we don't have that information, So in the simulation or in the modeling process, how do you think we should address this problem or this challenge? We can assume, everybody take the same practice, and so that you make a simulation. Yeah, that's probably most people can think of it. But that probably will not really, produce meaningful results, accurate results, I mean, So is there any way, if things that we know that some output in the reality, right? So from historical, let's say a county or a state, what is the yield of the, of the corn? Then is there any way you think about we can reverse engineering to predict that, or we can identify that basic practice, the management practice, so that we can get some sense the usual practice of the farmer for our modeling.
Yeah, thank you very much, Jeremy, for this challenging question. Well, let me do my best. You mentioned the word of reverse engineering or reverse. Indeed, that is the answer probably I like best. That is through reverse engineering. That is, in order to do, well, we know that simulation model can predict very well things like yield. But to do that, you need several fundamental accurate input information. For example, the planting date, plant population, and so on. Okay. However, I know that USDA NAS is responsible for making yield predictions for the country at the regional level. However, to get good results, you need the so-called bottom-up approach. That is, if you know the yield of every field, then you add up. This result would be a lot better than assuming, for example, the whole county or even whole state situation. However, to do that, you need to know a specific information about the specific field. However, we cannot ask every farmer to do it. The way probably we can try is using remote sensing and reverse engineering to backtrack to what situation would it be in the beginning of the season. For example, right now, let's assume it's end of May or early June. The crop has already established. Using remote sensing, we can estimate the canopy size, if area index. Through that one, and through the past weather data, we can simulate backwards to see when the plant is likely planted in order to get such canopy size now. So through this kind of trial and error, since simulation can be done very fast, and then within fraction of a second, probably we can figure out with a good certainty when the crop is likely planted and what probably is the plant population. I think probably that is at least one way of tracking back to the beginning of the season to see what kind of a situation is in order to provide a good input information if we use simulation to predict the next or the future or the end of season. So I think that's probably at least one way of doing it.
We may have two short questions because there are waiting two questions. Thank you, Haishun, for your answer, and thank you, Cankbey, for your question. Professor Altılar, Turgay Altılar, first.
Okay, thank you very much. Thank you very much for your speech and presentation, Professor Yang. I would like to make a comment initially. Maybe this would be the partial answer to Berk's question as well. When we're talking about digital twins, we are from different backgrounds. I'm basically from the background of computer engineering, so that from the perspective of computer engineering, when we are talking about digital twins, it means that in some literature, it's called digital twin instance, which means that there's a relation and interaction between the real system and the model. And as far as I can see, what you have done is called, again, in broad literature, is called digital twin prototyping. So that prototyping is, yes, can be considered as a simulation and modeling and simulation, but from the perspective of computer engineering, we usually tend to say digital twin to mean digital twin instances, and as well as aggregation as well. So that I would like to clarify this, hope it helps. The second point is a question, actually. You have given us 4 different examples. One is for watering time. The other is nitrogen requirements, population versus yield performance, and best planting time. My question is, how did you single out the impact of other contributors to the system? So that how would you measure the population versus yield, for example, given that there might be different weather conditions, different irrigation conditions, etc.? Thank you very much.
Well, thank you for the comment and for the question you have. Actually, for example, this plant's population, it's very interesting that many years ago, farmers knew already that increasing plant population will increase your yield. However, it also depends on other factors like nutrient availability, water availability, as well as your crop characteristics. Because when you increase plant population, you increase the intensity of plant computation among themselves. And how much a single plant or individual plant can handle computation. The computation for resources differs among the cultivars. So from that perspective, actually, it is cultivar related as well as the plant environment related. Environment including nutrient availability and water availability. For example, the same plant population may provide you a very good yield if it's fully irrigated. However, if water availability is not there, then the higher yield can crush the high plant population can crush your plant because the water can be used up early on before reaching maturity. You see, so that's why actually when you study the single factor, actually you have to consider other factors in this environment in order to evaluate its importance, its contribution, or its sensitivity to the final outcome.
Okay, thank you. And Ömer Vanlı,
Thank you.
Have you a question? If it is possible, it should better be shorter.
Okay.
Hello, everyone. Can you hear me?
Yes,
we can hear you.
Yes. First of all, thank you for your presentation. Actually, by the mean, I have been in the Wageningen University in 2015 to taking a course about art of modeling. Then I went to the United States to work on the DC set with Gerrit Hugenboom. Actually, it's very beneficial presentation. Again, I want to thank you. I have two questions, but one of them asked from Mr. Haishun Yang. The other question is, I just wonder that which the crop modeling program showing on your presentation. Can you a little give information about that? For example, is this program can calculate the crop coefficient, genetic coefficient, etc., something that. Other question is about regional yield estimation, but he asked already. Okay, thank you for everything.
Well, thank you for the question. The first question is, yes, I'm familiar with the DSAT with the series maize, and the program I used in the examples actually is a Hybrid-Maize. It's maize specific, just like series maize. The reason I call it Hybrid-Maize is because it is a hybridization of typical Wageningen programs like Morphos and the series maize. Because these two almost like a parallel development of the pioneer crop models. And somehow they have not been combined. And when I studied this research 20 years ago, I found both of them have their strengths as well as their limitations. But if we combine the strengths of both, probably we can come up with a better model, better than series maize and better than the typical Wageningen models. So this is, and then for the genetic coefficient, yes, they are important, but the genetic coefficient in models like a DSAT, they indicate the potentials. Sometimes they are not very sensitive to the final outcome because in the real world, the processes are further limited by the real conditions. So from that perspective, the calibration of the genetic coefficients may not be that important. That in my opinion, in my experience.
Okay, thank you.
Thank you. Jangui, Dr. Jangui, Dr. Yang, have you a comment?
Yeah, I have just trying to follow Professor Yang's comments and answer. Yeah, I just wondering that is there any models that has been implemented that has the capability to simulate backward?
I'm not aware of, but I don't think it's that difficult. For example, let's say,
Yeah. The front end model engine wise, yeah, it's kind of you just the clock, reverse the clock, right?
yes, you just reverse it, and also we know that the answer is within certain limit. For example, for corn, corn planting day. As I said in my one of the examples, you cannot plant crop too early. You cannot do it too late. It's probably within the window of 3 to 4 weeks, and you can reverse it and see what comes close to what we have right now. So that probably is good enough, because at the end of the day, let's say the accuracy of the input information depends on the accuracy of the final outcome. If we can tolerate, for example, 5% of error, then yeah, we can see how much much of error we can tolerate from the input side. Yeah, we don't have to be very precise.
Yes.
Thank you, Jangui, for your comment and the question. Haishun, we have really been appreciated your participation as our presenter today here. It was an enjoyable talk afterwards. And I thank also to all participants for their having existence here and their valuable questions. And hope to see you again our next webinar 2 months later, second Monday of the month. So I again thank you, and here for Istanbul, good evening, and in United States, have a nice day there, and good night in China. Hope to see you in our next presentation. You are always welcome. Thank you.
Thank you.